Okay, this is section 7.4. This is part 1, and we're going to talk about arc lengths. This is going to be sort of related to what we have been doing. Again, we're going to be doing the slice and dice type of techniques. Let's take a look at a typical type of problem where we're going to approach this with calculus. And we've got a curve, let's say, which looks like this. And I want to find the arc length. And this is y is going to be some function of x. I want to do it between a and b. So essentially, what you're doing here is arc length means you're going to start at a and then travel along this curve, and it's the distance you will travel. So arc length is the distance you'll travel along the curve, starting at point A and ending at B. So one way of thinking about this is we're essentially going to break this into a bunch of little small pieces and work through this thing. Okay, now these things are related to a formula you should remember from geometry, which is it's related to the distance formula, where distance equals square root of x2 minus x1 squared plus y2 minus y1 squared. And this thing came out of Pythagorean theorem. Okay, so if we come back in and we take a look at our little guy here. So what I'm going to do is I'm going to take one small part of it. I'm going to start at x sub I and go to x sub I plus 1. Okay? And I'm going to connect these with a straight line. I'm going to approximate this curve with a straight line. So basically, the distance along this little piece of my curve on that straight line is going to be the square root of, and it's going to be x sub I plus 1 minus x sub I squared plus y sub I plus 1 minus y sub I squared. And that's an individual piece. It doesn't matter where it is. This is just an individual little piece of this thing. Okay, now if you remember, delta x is defined to be x sub I plus 1 minus x sub I, and delta y is y sub I plus 1 minus y sub I. So my little bitty piece, distance, then is going to equal to the square root of delta x squared plus delta y squared. All right? Now, obviously, the actual piece we've got is going to be a little bit bigger because we have a curve, whereas this is using a straight line. But we're going to start with this for right now. Now, obviously, the smaller our delta x gets, the better our approximation. And this should ring a little bell of limit as delta x goes to 0. But we're going to do something before we get to that point now. So what I want to do then is I'm going to divide both of these. So I'm going to divide by delta x squared. And you'll see why here in just a bit. The reason we do this is it gives us something in a form that's going to be nice. So delta x squared divided by delta x squared gives me 1 plus delta y squared over delta x squared. or square root of 1 plus delta y over delta x squared. All right, when you're dividing like this, you can either do the quotient and square it, or you can square each individual part of it. Now, you should remember from Algebra 1, in geometry, Algebra 2, and pre-cal, and the first semester of this course, that delta y over delta x is slope. Okay. So I've got the slope for each individual little piece now. And now what I need to do then is, if I want to find my total slope all along through here, it's going to be the sum of each little piece we got, of each individual little piece, which is defined to be this thing right here. Okay, now I talked about the fact that to get this better, we want my delta x to get very, very small. So what we're going to do then is take the limit as delta x goes to 0 of my di. And if you remember, so then that's going to be the limit as delta x goes to 0 of the square root of 1 plus delta y over delta x squared. All right, so when I take the limit as delta x goes to 0, you should recognize what happens over here. That's going to be the square root of, now before I do that, let's review this, because this is a good thing to know. If you remember before I showed you the power rule and all the things, you had to go in and do all of this. But if you remember, the limit as delta x goes to 0 of delta y over delta x is defined to be dy dx, the derivative of this thing. So basically when I do this then, it's going to end up being square root of 1 plus dy dx squared. And that's the length of a very, very small piece of the arc. So that's going to equal to the length of a very small piece of the arc, or the curve, essentially, that we're trying to find the length along. That's a very, very small piece of it. And so now, to get the total part of it, we're going to integrate from a to b of the square root of 1 plus dy dx squared dx. And this is the formula you're going to use. I'm not so much interested in knowing how to derive this. However, for what I am interested in is you understanding where this comes from. It's come from the distance formula, and then taking the limit as my delta x goes to 0. Or, another way of looking at it, and it depends on how you feel about it, this, if you remember, is the length of a very, very small piece. And it would be a line. So it's the length of a very, very small piece of this thing. And then to get the total thing, we're going to integrate all these little bitty small pieces, an infinite number of them. And that's where our integral comes in. And this is the formula for arc length. Okay. So let's do a really easy and a really stupid example, but it serves to illustrate what we're doing with these things. Okay, so I want to find the distance between 0, 0 and 512 using the distance formula, which is the right tool for the job. And B, calculus, which is not the right tool for the job. But it'll illustrate how all of this thing works. Okay, so let's do part A first using the distance formula. So this is going to be 0.1. This will be 0.2. So the distance then is going to equal to the square root of 5 minus 0 squared plus 12 minus 0 squared, which is going to equal to the square root of 25 plus 144, which is square root of 169, which is 13. So that is our distance from using the distance formula. Okay, now on this one we have to actually do a little bit of cogitating and thinking about calculus. So let's take a look at what we're doing here. So I've got a point here, that's my point A. I've got another point up here. And we're trying to find the distance between these two. And so if you think about it, the distance between these two is going to be a straight line. So we need to find the equation of the line. And this is 512, and this is 0, 0. So my slope then is going to be 12 minus 0 over 5 minus 0, delta y over delta x. Well, my slope is 12/5. Now we're going to put this into point slope. So I'm going to have y minus, and I want to use this point because it's going to make my equation nice and easy. 0 equals to 12/5 x minus 0, and when I simplify this out, I end up with y equals to 12/5 x. And this is the curve. In other words, this is the equation for this line right here. Okay, so now we're ready to do our calculus on this. So there's my y. So the distance then is going to be the integral, and I'm dealing with 0 to 5. So it's going to be the integral from 0 to 5 of the square root of 1 plus dy dx squared dx. We need to find dy dx. So dy dx equals to the derivative of this, which is 12/5 period. That's my dy dx. So now we put all of this in. So my distance is going to be the integral from 0 to 5 of the square root of 1 plus 12/5 squared dx. So distance is going to be equal to integral from 0 to 5 the square root of 1 plus 144 over 25. Get a common denominator, and this is going to become important when we deal with more common ones. Anytime you end up with this, we're going to end up with a common denominator, which will be 25. So distance is the integral from 0 to 5, the square root of. Common denominator is 25, so I'm going to have 25 plus 144. Okay, so here's an important little rule to know. This is the same as the square root of 169 over the square root of 25. You can break up multiplication and division. which is going to equal to the integral from 0 to 5 of 13 fifths dx, which is going to equal to 13 fifths x, evaluated from 0 to 5. And most of you should see where this is going. So that's going to be 13 fifths times 5 minus 0, which equals to 13. And we get the same number. Okay, now the whole point of this was not so much that you should use calculus to find the distance between 2 points, because you shouldn't. The whole point of this was to illustrate how to do all of this. And I also want to make sure you understand getting common denominators. That's going to be very important. And also breaking up the square root of the numerator and denominator. That is also going to become extremely important. Well, your exponent rules are going to be very important too. Okay, so now let's deal with a little more realistic example. So we want to find the arc, or the arc length between 1 and x equals 1 and x equals 8 of y equals 3/2 x to the 2/3. Okay, now this is one where we're going to have to use calculus, because this is kind of a strange puppy. It's not a straight line at all. Okay, so we've got our y. The first thing we need to do is find dy dx. So to do that, first thing you do, remember, you take a derivative, is you multiply by your power. So I'm going to have 3/2 times 2/3. And then I'm going to subtract 1. So it's going to be x to the 2/3 minus 1. These are reciprocals, they're 1, so that's going to give me x to the negative 1/3 is my derivative. Okay. So now we come in then and we plug all of this into our formula. So the distance, our arc length, is going to be equal to the integral from 1 to 8 of the square root of 1 plus x to the negative 1/3 squared dx. Okay, now we're going to have to apply some exponent rules. And if you remember, whenever you raise an exponent to power, you just multiply them. So d is going to equal to the integral from 1 to 8 of the square root of 1 plus, I'm going to have 1 over x to the 2/3 dx. Remember, the negative means inside. Okay, now if you remember on the numerical example, I got a common denominator, and that helped me. But let's go in and take a look at this thing, and I'll show you why you need to do it. Now to integrate this thing, your first instinct should be to use substitution. So in that case, if we use substitution, u would be 1 plus x to the negative 2/3, which means du would be, that's 0, so it would be negative 2/3 x to the, and then subtract 1, negative 5/3. Now, we can live without that, but you notice I don't have this in here, which means we cannot use substitution. All right? And also, this doesn't really work out really well for the inverse trig functions. So what we do on these, then is what I told you we did before. We're going to come back in, and we're going to take a look at this thing, and I'm going to get a common denominator on it. So my common denominator, so let's come back up here then and rewrite this thing. It's going to be the integral from 1 to 8 of the square root of 1 plus x to the negative 2/3, 1 plus, I'm going to rewrite this, 1 over x to the 2/3 dx. So now I'm just going to concentrate just on this part of it right here. So my common denominator, my least common denominator, is going to be x to the 2/3. So I'm going to end up with a square root, and I'm going to have an x to the 2/3 below it. And then that was going to give me x to the 2/3 plus 1. Now remember, I told you could split these up. So it's going to be the integral from 1 to 8, and you'll see why this is slick here in just a bit. It's going to be the square root of x to the 2/3 plus 1. And no, you cannot take the square root of both of these. Will be over the square root of x to the 2/3. However, something nice is going to happen in the bottom. So I'm going to rewrite this thing. It's going to be the integral from 1 to 8, the square root of x to the 2/3 plus 1 over x to the 2/3 to the 1/2. Now, all I did was rewrite my square root as the power of 1/2. So distance now is going to be integral from 1 to 8 of the square root of, I'm going to rewrite this as a power. So now I'm going to have x to the 2/3 plus 1 to the 1/2 over, and remember when you raise it, you just multiply it, so it's going to give me x to the 1/3. So I got rid of my square root on bottom here. So does this help us? Well, we don't really know yet, but remember I went in and said we were looking for a u sub. So let's see now. We did not have one in the form we had before, rats. Let's see if we've got one in this form. So here we go. Here is my equation that I've got. So I've got d will be equal to the integral from 1 to 8 of x to the 2/3 plus 1 to the 1/2 dx over x to the 1/3. Alrighty. So my u then is going to be x to the 2/3 plus 1. Du then will be 2/3 times x, and you subtract 1, it'd be to the negative 1/3. And right there is our x to the negative 1/3. We got it. Okay, this is nice. Now what we don't have is this 2/3, but I can take care of that by multiplying by its reciprocal outside. So it's going to be 3/2. And now I'm going to have the integral from 1 to 8 of u to the 1/2 du. This one we can integrate nicely. All right. So you add 1 to this, that gets me 3/2. And then we take the reciprocal. So d will be 3/2 times reciprocal of, I'm going to end up with u to the 3/2 here. I have to multiply by the reciprocal of that. Okay? And this is going to be evaluated from x equals to 1 to x equals to 8, which we don't have right now. So I'm going to plug back in. Notice these are reciprocals, so now I've got my distance is equal to, I plug back in for my u, which was, where was my u? It's back up above me. X to the 2/3 plus 1. So now I've got x to the 2/3 plus 1 to the 3/2, and it's going to be evaluated from 1 to 8. So now I just plug these numbers in. So that's going to equal to 8 to the 2/3, which is the cube root of 8, which is 2, squared, which is 4, plus 1 to the 3/2 minus, and then I've got 1 to the 2/3 plus 1 to the 3/2. So now I evaluate all of these things. 8 to the 2/3 is going to give me 4 plus 1. It's going to have distance is going to equal to 5 to the 3/2 minus 2 to the 3/2. And if we plug this in, it's going to be, if we round it out to 3 decimal places, it works out to be 8.352. All right? This looks a little bit intricate, but I'm going to make a point here. The trick to integrating the square root is find a common denominator. Then take square root of top and bottom. Now you want to look to see if you can either break this thing up or if you can get a u sub. Okay. So let's take a look at one which handles a little bit differently, but you use the same rules for, all right? And it sort of illustrates the point of keeping your wits about you when you do this. So what we get, this is our next example. And this is one where you're definitely going to need your big girl panties, because y equals to x to the 5th over 10 plus 1 over 6x cubed. And we're going to integrate it over the closed interval 1, 2, 2. Okay, first time I saw an example like this, I really thought I was going to wet myself. It was kind of like, oh my God. Okay. And so I freaked out. I would run into a little help session. The graduate student sat in there and says, come on, stupid. The first thing you do is find dy dx. Well, I could do that. So I need to take the derivative of x to the 5th over 10 plus the derivative of 1/6 x to the negative 3. All right, well, I could do this. This is just simple power rule. All right. So I multiply by, I'm going to this term too, multiply this, so I'm going to end up with 5/10 Now subtract 1, x to the 4th, plus, I thought, no, it's a minus because my coefficient, or my exponent is a negative. It's going to be minus, multiply that down, so I'm going to have 3 over 6, x to the negative 4th, and then I'm going to go ahead and rewrite this, so dy dx is going to equal to x to the 4th over 2, that's simplifying that, minus 1 over 2x to the 4th. Okay, and remember we're going to plug this thing into a big cowabunga thing of 1 plus dy dx squared. So the trick to these kind of things is to go ahead and see if we can do something about this to begin with. So I'm going to just deal with the inside part of this for now. I've got a 1 plus dy dx squared. All right, well here's my dy dx squared. So the first thing I'm going to do then is I'm going to have a 1 plus, and then I'm going to have this whole thing, x to the 4th over 2 minus 1 over 2x to the 4th squared. So I know the first thing I'm going to have to do is get a common denominator inside here. And my least common denominator is going to be 2x to the 4th. All right? You should see a pattern here. Common denominators, common denominators, common denominators. So I'm going to have a 1 plus. And then I multiply. To do this, I'm going to have to multiply the top and the bottom by x to the 4th. And my denominator down here is going to be 2x to the 4th. Square that. Again, with the squares, we can pull them out. And then this is going to give me x to the 8th minus 1. Squared. Okay. So what I did here now then, again I know I'm going to need a common denominator. So everything is going to be over 2x to the 4th squared. So now I've got this thing, so I've got a 2x to the 4th squared plus, and I'm going to go ahead and expand this thing right here. Yeah. So when I expand that, I'm going to end up with x to the 16th minus 2x to the 8th plus 1. Or I'm going to end up, when I square this, it's going to give me 4x to the 8th plus x to the 16th minus 2x to the 8th plus 1. And that's all going to be over my 2x to the 4th and then I'm going to combine my like terms, so I'm going to end up with an x to the 16th plus 2x to the 8th plus 1. All that is going to be over 2x to the 4th squared. Now if I could write this as a square, I've got it made. So let's take a look at this. So this is going to be x to the 8th squared plus 2x to the 8th plus 1 over 2x to the fourth squared. And so this can be factored, all right? Should be x to the 8th. So I've got it x to the 8th squared, so I'm going to end up with x to the 8th plus 1 squared over 2x to the fourth squared. And remember, that's going to equal to my 1 plus dy dx squared. Okay, so your question is, why the hell did we do all of this? Let's pop back into our original formula, and you'll see why. Because our distance, if you remember right, is the integral, and we're integrating from, God, I forgot where it is, 1 to 2, of the square root of 1 plus dy dx squared. All right, so I've got this part right here. Now you notice I've got a square root in there, but look, I've got a square on the top and a square on the bottom. So this is going to make this thing possible. So my distance then is going to be integral from 1 to 2 of, I'm going to have the square root of x to the 8th plus 1 squared over square root of 2x to the fourth squared. Now you see why I didn't do that. The squares and the square roots cancel each other out. So now d is going to be equal to the integral from 1 to 2 of x to the 8th plus 1 over 2x to the fourth. Okay, now I still don't have a u sub, but it's all right, dx, because now I can split my numerator up. So distance is going to be equal to the integral from 1 to 2 of, and remember you can split up numerator but not denominator. I'm going to have x to the 8th over to the 8th, 2x to the fourth, plus 1 over 2x to the fourth. Dx. Our distance is going to be the integral from 1 to 2 of, when I simplify these, it's going to give me x to the fourth over 2 dx plus the integral from 1 to 8 of 1/2 x to the negative fourth dx. Okay, so now we can do these things. And like always, I'm going to pull my constants out. So I'm going to have a 1/2. And I've got a 1/2 in both of them. So we'll have 1/2 times the integral from 1 to 2 of x to the fourth dx. Well, that's a simple little rewalk. Plus the integral from 1 to 8 of x to the negative fourth dx. This is also a simple little rewalk. So I do it. I'll have 1/2 times all of this. And I'm going to add 1, so I'm going to have 1/5 x to the fifth evaluated from 1 to 2 plus, except now I'm going to have a negative. So when I add 1, I end up with a negative 3, so it's going to be minus 1/3 x to the negative third evaluated from 1 to 2. Or it's going to be 1/2 x to the fifth over 5 evaluated from 1 to 2 minus 1 over 3x cubed evaluated from 1 to 2. And I'm not actually going to go in and do all of that, but at this point you should be able to plug all of these things in and get your answer and get it out. So again, the whole point here is common denominator. Once you find your dy dx, square it, get a common denominator, all right? Now, I didn't go back in, I should have shown this to you, but let's go back to where I first got my dy dx. Which was right here. Okay. And when I got my common denominator, you notice I ended up with this thing down here. I would end up with 4x to the 8th. Now, the reason I didn't go ahead and u sub at that point was I still did not have a u sub on bottom. And when you don't, then the best thing to do, when you still end up, you get your common denominator, and you don't have a u sub, is to go ahead and expand this stuff out like I did and add 1 to it. And then try to write this thing where you've got a square on top and a square on bottom. And that's going to make things so much easier and so much nicer. Because that's what I ended up with over here once I did the whole stinking kit and caboodle. Was I end up with square on top and bottom, and then the square roots canceled them all out. So again, take a look. Always see if you can do a u sub. If you can't, remember to come back in then and get a common denominator for your 1 plus inside and try to write them as a square on the top and a square on the bottom so that your square root goes away, and now you've got something nice and easy and plain to work.